And then welcome to lecture number 2 in CFD, Introduction to Lattice Boltzmann Methods. So this means lecture 2 means we have covered some space on the kinetic theory on which we based the Lattice Boltzmann method, and the last few things that we discussed last time here were, the Lattice Boltzmann, we were starting with the Lattice Boltzmann methods. We've said that the Lattice Boltzmann method, even though it is based on the Boltzmann transport equation, is actually there to solve the Navier-Stokes equation. And so what we do is we solve we discretize the Boltzmann transport equation in a very simplified fashion, namely in such a way that it is just compatible with the Navier-Stokes solution and not necessarily with the entire kinetic domain. So the Navier-Stokes equation is obtained from the Boltzmann equation at the first order in Knudsen number. So we do a first order in Knudsen number discretization of the Boltzmann equation and expect that then we'll get something that solves the Navier-Stokes equation. And here's the example for this in 2D with regard to virtual fluids. Again, virtual fluids does not allow you to do simulations in 2D, it's only 3D, so you can expect this to look a little bit different than that one. And it's just the tensor product of this. So what we do is we take very few discrete speeds with which we discretize our velocity space, and these discrete speeds, they are on what we call a lattice. So this is this crystallographic like structure here, and the reason for taking this kind of lattice where particles move in each direction with a constant speed, as for example compared to we could also put this on a kind of a circle, right? So that all of them would have the same energy. Now these don't have the same energy because this here has a smaller magnitude of velocity than this one going in the diagonal. Yeah, but the reason why we do this is because if we have this discretization of the velocity space, we can map this in the spatial physical, what we usually call space, just by saying a particle within a certain time moves from one point to another point, and we can now discretize the spatial space according to our velocity space, so that particles just always in one time step move from one point to another point. Yeah, so this requires this lattice structure. Yeah. Okay, and in 3D, of course, we have 27 of these. So, and yes, and then we discussed the Boltzmann, the lattice Boltzmann equation, which looks like this. So we have a pre-collision state Fij, so this is the indices are for the different directions. And so what we write without any annotation here, this is always our pre-collision state, and the thing that we write with the asterisk up here, this is the post-collision state. And these are, so the distinction between them is very important, as we'll see later in this lecture here. Another thing that we do is a little bit modern interpretation of the thing is that we regard this not at the lattice nodes and not at the time steps, but in between the grid nodes and in between the time steps. Yeah? So this has some advantages, which in this lecture will not discuss too much about it, but the thing that we want to obtain is by this method we can make the update rule symmetric both in space and time. And when if you know something about numerics, you know that if you have symmetric discretizations, they are always one order better than if you have non-symmetric discretizations. Yeah? This is why you should always try to use centered finite differences and centered time integration. Yeah? So actually having centered time integration is very, very difficult normally in numerics, but Lattice Boltzmann has centered time integration, which is a particular advantage. Okay, so then, yes, we said that the algorithm is simple. Two things that may be not so simple is the use of non-Cartesian grids, and everything here is transient, which can both be an advantage or a disadvantage. So if you are interested in any steady state simulation, then you probably have to run this through time update, and if you are interested in a very slow process, this can be very complicated. I should mention there are solutions to these things, so you're not. So this we can also solve the Lattice Boltzmann equation in a different way in order to get a steady state, but this is not the usual way of doing Lattice Boltzmann. So. Okay, so this was the recap of what we did last week, and now we come to the understanding how Lattice Boltzmann actually works. And we start with the macroscopic quantities in LBM. So, I mean, one important thing is, if you use this kinetic method in order to solve the Navier-Stokes equation, we need to know how we compute our Navier-Stokes solution from the solution of this Boltzmann equation, because you know that our variables here are not the velocity and the pressure, but the distribution function f. So, since both ways solve the same problem, the same physical problem, there must be a way to get the macroscopic quantities, so velocity and pressure and potentially something else, from this distribution functions. And the way we get these are from so-called moments. And these moments they are not defined that way. This is probably, but they can be computed that way. I come to how they are defined. So we call them what I call countable moments. And this is M is for the moment, and then this thing has three indices, A, B, and C, because we are in 3 dimensions. And I write this C in a particular fashion because I'm running out of letters, unfortunately. Yeah. So we can compute this in a discrete fashion when we sum. So this is actually a triple sum. Yeah, but I write it this way over the indices I, J, and K, which are the indices in the different velocity directions, over the population F, I, J, K. And here comes then C. So C is the lattice speed. Yeah. So this C. So this C here is an index because A, B, C. Okay. Could have A, alpha, beta, gamma Yeah, but I wrote it this way. So this here, C without the Klüfen, is the lattice velocity. This goes by the power of A, Cj by the power of B, and Ck by the power of the other C. Okay? So these are, say, like statistical quantities. Of the distribution. So a few things to remember, because we are going to talk about this. There is an order of a moment, and the order of the moment is the sum of its indices. So the zero order, there's only one zero order moment. Is the mass, so m000, and this is written as rho. So now I'm a little bit in trouble here because this is not completely consistent. So each field in science has, you know, its own culture and its own floppiness, and here is some sort of floppiness. So rho usually means the density because it's the mass associated with a point in space which you could imagine covers some, okay, point and volume is, you know, there's the sloppiness already, yeah, but there is a cell around this point, and within this has a volume, and the mass then divided by this volume is the density. So we say sometimes density and sometimes mass, because it's the mass associated with this small area around it. Okay, this is part of the sloppiness here. And we call this thing rho, even though we should call it m. But you will find this in literature this way. So the first order moments, of which we obviously have 3, this is the momentum. You see, we sum over the velocities here. Yeah? So these are velocities. So what we get out is m100 is rho times ux. So ux is the solution from the Navier-Stokes equation. Yeah? m010 is rho uy. This is the other solution of the Navier-Stokes equation. And then you have m001 is rho uz. And we can also get the pressure out of this, and this looks a little bit more ugly. So the pressure, in principle, is a second moment. There are many second moments. So we can write the pressure as being the sum over I jk, Fijk. So we have Ci minus ux. So you see, it's starting to look a little bit, so it's not so straightforward, apparently. Cj minus uy squared plus a ck minus uz squared. Okay, so this is the way you actually would have to calculate the pressure Nobody does it this way. So pressure is often computed from the equation of states. And this is P. P is given as Cs squared, so the speed of sound square times the density. Actually, it's interesting. If you study fluid dynamics in more detail, then you will find that there are plenty, I think it's still order one, but like 4 or 5 definitions of pressure which are all not exactly the same. Yeah. So this is this here is the thermodynamic pressure. So they are to a low enough order, they are the same, but they are not exactly the same. So doing this gives you almost the same as doing that. Almost. Okay, so these are the macroscopic quantities. Then what are we doing with this? We are doing collisions. And now what? Yes, please.
But why we write this as this like Ci minus Ux, like in this form square, like the pressure is the second moment.
This up here.
Yes, is it from like already in this form or just wait like
Why?
Assume that?
Okay, why do we write? You know, in my opinion, there is a historical reason to this. So, as I told you last time, we know about molecules since 1905, right? So, but the idea of pressure is much older than that. So pressure, also since then we know what temperature means. So people had an idea about pressure and temperature before, and they described these in their equations. And the question is, what do these things, temperature and pressure, actually correspond to in the microscopic world? Yeah? So the thing that if you do the expansion to the mathematical analysis of the Boltzmann equation that transits to the Navier-Stokes equation, and then you ask yourself, how can I match these things that appear in this equation and in that equation? Then you will find that this here appears in place of the pressure. However, there is a catch, namely that some parts that appear in this are actually of order higher than would be necessary for the Navier-Stokes equation. So meaning, or at least for the incompressible Navier-Stokes equation, meaning that this is not uniquely the pressure. There are other things that are also the pressure. Yeah? With their difference being small enough though that they don't appear at the first order in Knudsen number. And therefore, there is not a completely unique definition of pressure. Okay, I was not expecting that you like this. So, a few things about collisions. What do collisions do? So we are not doing molecular dynamics here. So we already have this distribution functions, and we want to see what collisions do to the distribution. So collisions drive. Okay, collision. Okay, the collision. Yeah, the collision drives the distribution. The distribution F towards equilibrium. Meaning that the population after the collision is closer to equilibrium than it was before the collision. In order to see what this means, of course, we have to define what is actually equilibrium. So I have an entire lecture on this in my other course, but here we have to be a little bit more compact. What do you think is equilibrium?
Stable state.
Yeah. Right, so this is a state from which you cannot escape. This is actually the definition. They're very good, but it doesn't tell us how it's how it's made up. So equilibrium comes from the comparison between macro and micro states. Yeah, if you remember your what is this, thermodynamics class, yeah. So equilibrium is only defined in the macro state as the macro state with the largest number of realizations, and the realization is a microstate. Largest number of okay.
This realization means this like a cycle to reach that state?
No.
No?
Okay, I have some comparison with microstate and macrostate. So this is always done with some stupid example, and you have to do the comparison to real physics. So my stupid example here will come from coins. Yeah. So and the important thing here, why we can do this in kinetic theory, is because we deal with undistinguishable particles, while the reality has distinguishable particles. Yeah. So the thing with microstate always uses distinguishable particles or entities, and macrostate uses indistinguishable entities or particles. So in the microstate, you have configurations of a system of distinguishable particles. This is the microstate. And now you can, if my particles are coins, we could have something like this. So we have one coin showing a number, another coin, and you see this other coin looks different. This is showing a face. Okay. Or you may have a coin like this. I don't think that coins like this exist, but anyway. Maybe in some place we have square coins. Yeah. So what I want to say, all coins are individuals, and all coins are either, up or down. Yeah. And each of this configuration here has the same probability. So you throw them up, they fall down, and they have any, they come down in any way, and all of the ways have the same probability. Now compare this to what this means for the macrostate. There's a configuration. Macrostate is a configuration of system of undistinguishable. So this was distinguishable, and now we are in undistinguishable. Particles. Now, okay, all of them have the same configuration that you have on the other side, but you cannot distinguish them anymore. Otherwise, they look all the same. Yeah, and here you will have a 50% head. Say the face is the head for me now. This has the highest probability. It has the highest probability because it has the most number of microstates that lead to that macrostate. These are the realizations. Yeah. So each for example, one thing that is particularly unlikely is that all coins that you throw up come down with the head, because there is only one microstate, yeah, that reflects this. The same is with all coins showing the number, because there's only one microstate that would realize this macrostate. Yeah? But coins being equally distributed between heads and numbers, this has the highest number of realizations. So if you have a very large number of coins, you throw them up and they fall down, then each micro configuration has the same probability, but if you just count how many heads are showing up, then it's very likely that this will be very close to 50%, because this has the highest number of micro realizations. So, and this is what we call the equilibrium then. So the highest, what's the time? Highest. So the highest probability for local Okay, so this is one important thing. Local velocity. So this turns out to be, as with many statistical things, it turns out to be a Gaussian distribution. With the mean, so the mean is the first moment, right? The mean is the macro, the macro velocity, and the variance is related. So this is again a little bit stupid because there are these multiple definitions. So it's related to the pressure, temperature, or the speed of sound squared. So these things are all connected. Temperature, pressure, and speed of sound. These things are all connected to each other. One important thing to know here, this is the local. We are talking about the local equilibrium, which I remember to physicists is a concept that is very difficult to grasp. So because there is this global equilibrium, which is what the physicists call the heat death. Ever heard about the concept of the heat death? So this is the idea when entropy increases, then everything goes to one global equilibrium in which all energy has become heat. Actually, this situation would be pretty cold in reality, yeah, but it's still called heat death because all energy is then heat, yeah. So, and this is the global equilibrium where we take everything into account. A local equilibrium is just you look into a very small volume, but which is still large enough such that there are enough degrees of freedom that you can make this statistic, yeah, so that you can define an equilibrium. Actually, there's a problem with this because saying local would mean it is one point, yeah, but in one point there are no, I mean, there would be no atoms in one point, yeah. So there is here we have a kind of an uncertainty principle applying, yeah. So this thing needs to be small, but it needs to be not too small in order for it to contain nothing. Yeah? And this is, as you remember again, so this is now related again to the Knudsen number. Yeah? So this is true for Knudsen numbers being small. Yeah? Okay.
That's why it is really, and I heard that it's really hard to understand the concept of this entropy, because it's very difficult.
The concept, you heard that the concept of entropy is hard to understand. Is the concept of entropy hard to understand? I mean, you can go to YouTube, my first lecture in the Lattice Boltzmann course, and there I explain entropy, and then you can come back and tell me whether this was hard to understand. Entropy is at least insofar hard to understand that it was defined. So entropy has the same problem as all the rest of this. Entropy was introduced somewhere, I believe, in the more like in the beginning of the 19th century, without long before the concept of the atoms and so on. So it was only later identified. So it was only later identified in thermodynamics. The entropy in thermodynamics does not care about molecules. Yeah. So Boltzmann's, so the equation that is written on Boltzmann's tombstone. Yeah, this is the one that he used to prove he was proving the direction of time. So Boltzmann actually introduced a function ether, which then turned out to be the negative entropy. And he derived this from his equation, from the Boltzmann equation, and there, if you understand this, I would claim that you potentially understand entropy. But you had to identify, so actually they had to identify entropy with this thing. Yeah? So you come from two sides and then you see, now there's a connection, I just have to put a minus sign in front of this and then I have the same quantity. Yeah? Because entropy can be understood from these two directions. Because it was introduced from macroscopic idea of something driving what is actually defined. It's the reversible work divided by temperature, if I'm not mistaken. Yeah, this is entropy, and this somehow connects from the other side to how many microstates are in one macrostate. Yeah? So this is actually entropy. How many microstates are in one macrostate? Yeah, and actually, so but it's not directly this, but it's the logarithm of the number of microstates. Yes. Okay, sorry, I didn't want to talk about this. Where are we?
Local and global.
Yeah. So okay, there's this local. Okay. The problem is that equilibrium is defined as the state with the depends on whether you're a mathematician or a physicist. Either it's the maximum or minimum entropy, so it's the least entropy, if you will, and this is only defined for the entire universe. Yeah. So now we have to cut out a small piece of the universe and say, so when this was all of the universe, what would be their maximum entropy? And this local equilibrium this can be computed from the local conserved quantities, because it has the mean. Its mean comes from the velocity, and its variance comes from the pressure. And the pressure is also related to mass. Mass, momentum, and in principle, but not here, energy. Okay, so there's a little bit of strange thing, but we do not take energy into account. And the reason why we do not take energy into account is that if you look at the Navier-Stokes equation, in the incompressible Navier-Stokes equation, unless you amend it with the Fourier equation, the Navier-Stokes equation does not contain energy. Yeah, and it also does not conserve energy. So if we discretize the Boltzmann equation up to an order that is just compatible with the Navier-Stokes equation, we have to give up on energy conservation. Because even though in nature energy is conserved, in the Navier-Stokes equation it is not. Yeah? So, now one example for this is the so-called single relaxation time. Approximation. This is actually implemented also in virtual fluids. I had to look this up yesterday and try it out whether it actually works. So we usually not using this, but it's also there. Though this is this idea is due to Bagnaga, Cross, and Krug, was a very international collaboration between an Indian and South African and an American back in 1954, and has actually nothing to do with Lattice Boltzmann, but it can be applied in Lattice Boltzmann too. So the idea is that the distribution transits to equilibrium on the time scale of one mean-free time. And the mean-free time is the time between two collisions. So what we had, so this here, this omega, again, is the collision. The collision, the effect of the collision, or the change in the population, in the distribution due to collision. This is what we call omega. Mathematically speaking, it's not exactly an operator, yeah, but you often call this operator. This is now assumed to be, there's a minus here, minus F equilibrium. So there is the distance between the population and its equilibrium population divided by tau. So this guy is called the BGK for Bagnaga-Cross-Krug collision. And now I've written this F with the overbar. So what is the F with the overbar? So this is not the way Bagnaga and Cross and Krug wrote it, because they were not concerned with discretization. They were actually looking at the real Boltzmann equation. Now in the lattice Boltzmann equation, I remind you, we actually have two Fs, namely the F before the collision and the F after the collision. Yeah, and an important question is, so for which of these do we actually want to solve the Boltzmann equation? And the right answer for this, for neither of them, but for something else. Namely, this is the F overbar, this is the distribution at collision time. So fun fact is we don't have them. We don't have this in the Lattice-Boltzmann methods. In the Lattice-Boltzmann methods, we have the distribution before the collision and after the collision, but we don't have it during collision. So how do we get to the population during collision? Yeah, well, very simple. We say, if we have it before and after, we say it's 1/2 the one before plus 1/2 the one after. Yeah? So this is, again, so this is pre-collision, and this here is post-collision. Okay, and now you can write these things. So the post-collision is the pre-collision plus, okay, something changes in time, so I have to multiply this with the time step, comes here omega, and then if this is the case, we can write this overbar version as 1/2 2f plus delta t omega, meaning that f can be written as f overbar can be written as as f plus delta t half omega, right? So omega can then be written as, so there's a minus in front, f. So because we don't have f over bar in our calculation, so we have to replace this f over bar by this guy here. So this is f before the collision plus omega 1/2 minus f equilibrium divided by tau. Okay, why is this cool? It's cool, so mathematics heart is pounding. It's cool because it's implicit. So the collision depends on itself. The collision depends on itself, and it's even cooler, namely we can resolve this dependency. So we can, because we can put everything that we want to know on the left-hand side, so we can write omega 1 plus delta t by 2 tau. So we bring this on the other side is minus f eq divided by tau, which means that omega is equal to minus f eq divided by tau plus delta t half. So
what you written in this equation is not omega delta t by tau, right? The second last.
This
F plus omega divided by 2 or delta t divided by 2 minus f eq. Omega equal to minus.
I kind of lost you. We are talking about what line? This line?
No, this one here.
This one here, yeah.
Delta t by 2. This one. The second.
So we take this equation up here,
Yes.
and we plug in this here.
Okay. Yeah, I mean everything is okay, but omega equal to minus f plus omega by 2 or delta t by 2?
Delta t.
Minus f eq.
Is there something that you cannot read or here?
Here is omega divided by 2 or
Omega.
delta t? It's delta t, right?
Wait, it's okay. You mean I've forgotten delta t? Yes. Okay, I've forgotten delta t.
It's delta t.
Okay, delta t by 2
Yes.
omega. Okay, yes, thank you. Yeah. So right, I've okay. Maybe I misspelled this on my note. So, but you see, then this comes out. Yeah. Okay. We repaired this. Okay, I just missed this here.
Now everything is okay.
Yeah. So anyway, I'm making here a small trick, and this is something that can easily escape everybody's attention. But this small trick here is extremely important, and because it is the reason why lattice Boltzmann works in the first place. So it should not be underestimated. The problem would be if we had written this equation up here directly with the f, and we would like to solve the Boltzmann. If we discretize the Boltzmann equation directly, saying f is the f in the Boltzmann equation, then we have this operator, and what you would see is if this time here is small, then the collision time is very small. So you would, during integration, you would integrate this over delta t. So basically you have delta t divided by tau. So if with delta t divided by tau, or tau is small, then tau is much smaller than delta t, then delta t divided by tau is very small, or is very large, so that this influence of the collision would be very large. And now imagine that tau is really, really small, because it's the time between collisions. So if you had then to physically resolve this time between collisions, then you would not be able to do anything with this method, other than, solving the Boltzmann equation itself. Now, in that case, the lattice Boltzmann method would be the most stupid thing in the world, because first, you would have to resolve the collisions between the particles on one hand, but on the other hand, your discretization is so poor that it can only solve the Navier-Stokes equation and not the real Boltzmann equation. So you would have a really, really stupid method. And nobody would use it. So, okay, maybe that's the reason why there are not so many students. I don't know. But lattice Boltzmann has been used for calculating the track on cars, so all cars that were built before the year 2000 or before the year 2010, all cars were simulated with lattice Boltzmann. It's only since there is open form that this kind of changed a little bit. Before that, all the cars were simulated with lattice Boltzmann. So why is lattice Boltzmann useful? The reason is here. You see, if now you multiply this by delta t, this here is never getting small. If tau is going to 0, that's not small. Which means there is no. Okay, we have by this simple discretization, we have thrown out the kinetic, the kinetic picture where we can do fancy things that are outside of the Navier-Stokes equation. But at the same time, we have also thrown out the restriction of it. So we have no kinetic restriction on the time step. That means we can simulate this as fast as a usual Navier-Stokes solver would simulate this. So this is a very, very important detail. Because without this, we wouldn't use it. So the time step can be much larger than mean free time. meaning there is no time step restriction from kinetic theory. So even though I'm wasting my time here, but I'm doing Lattice Boltzmann for such a long time that I can remember going to these conferences, and each year a new poor mathematician PhD student showed up with exactly the same idea as the ones previously, because apparently nobody told them. Whereas mathematicians do it the other way around. They come from an equation and discretize them. Now some physicists give some rules, and they say this. We analyze this, and we know asymptotically this solves this equation. And then the mathematicians say this is, this discretization is stupid. Yeah, because if you don't write it, this is why I immediately, to make this clearer, I immediately start from the symmetric discretization. Because you can also write this in a non-symmetric way, would do the same thing, and assume you're solving the equation not for f bar, but for f. Then you see this is only first order accurate. Then mathematicians think, oh, these stupid physicists, we can do this better. I know this and this Runge-Kutta method that discretize this in a much better way. So then they discretize this in a much better way. Everything is nice in mathematically, everything is nice. They are using the correct f here and end up with exactly this equation where they run into this time step restriction, where now they have a very high order discretization of this thing, but they have a physical time step restriction. Then they are a little bit confused. They go on a conference, give one talk, and next year they have stopped doing this and have chosen another topic for their PhD. And because they didn't write it down, next year will be a new student doing the same thing. Okay, sorry for this story, but I've seen this so often happening. So, yes, we in the virtual fluids, we are not, it's implemented, but this is not the way we usually do this in virtual fluids. In virtual fluids, we are using something that we call the superconvergent cumulant collision operator, which you can call in the method as, so this is, if you set, so you can choose different collision operators, and this one here you call with K17 compressible. There's also uncompressible and compressible Navier-Stokes. Here compressible, okay, I have compressible means weakly compressible, so it's not the really compressible Navier-Stokes, it just means that the density is dependent on that pressure and density are coupled. Yeah, so that density is not constant. This is what we call. So we flow, flowing together in one area, then the density will increase. As a little bit of a simplification. Okay, so this is what we are usually using here, and this is the reason why I have to talk a little bit about more detail about this collision operator. This in general and others No, this in particular and others in general. So, in principle, this is also true for the BGK collision operator. The collision operator hides the microscopic detail. Of the molecular interactions. So this is our simplification, and this also means that there are many different ways, many possible approximations to do this, of which the BGK is just one. So in principle, all of them lead to the Navier-Stokes equation. So from a certain philosophical perspective, they all are the same. But then you come to the question of convergence. So how quickly you go to the Navier-Stokes equation. And there they may be very different. So BGK, the idea of BGK, one part of the idea of BGK that we are going to keep here is that we know an equilibrium, we know the population that is coming in, and we say this population is going closer to the equilibrium. In BGK, there is only one time scale. So the idea that you could take here is that you draw a line in between, in any space that you could think about. You draw a line from your position here and the equilibrium, and the post-collision distribution will be somewhere on the line that you draw through these 2 points. So it's a one-dimensional thing that has only one relaxation rate. However, the entire population has many degrees of freedom, and in principle, we could also regard this as a multidimensional problem, where different quantities of this population have different time scales, and this leads us to the principle of multiple relaxation times. So, saying that different, now I just call these aspects without defining what this means, different aspects of the distribution function approach equilibrium at different rates, saying with different time scales. Actually, this is true in physics, because one thing that is observed if we use one single time step, relaxation time. So under the single relaxation time approximation, we have only one transport coefficient, so the kinematic viscosity, and for example the heat diffusion have the same value. So there are different diffusive processes in physics. Yeah? So viscosity is a diffusion of momentum, and heat conduction is basically the diffusion of kinetic energy, or microscopic kinetic energy. And in physics, we observe that these two things are not the same. So that the diffusion coefficient of heat and the diffusion coefficient of momentum, they are not the same, but if we attach a single relaxation time to the entire distribution, they are the same. So actually this this concept of a single relaxation time is not, you could say it's experimentally disproven. Yeah? It's not true. It's just a model. So then the reality actually would be that different things have different relaxation times. If we use different relaxation times, then we have also in our model the possibility to adjust transport parameters differently. Independently. So the question is how is this done? So if we have only one relaxation time, we do not need to think about any particular distribution. Okay, so if we have one relaxation time, then it does not matter how we actually measure our distribution. I mean, the distribution has somehow to be stated in some variables, yeah? And no matter whether we rotate them, whether we stretch and scale them, or in any other way, if we have one relaxation time, they would always behave the same way. Only when we have several relaxation times, we have to split these things up in a particular way that allows us to say, this has this time and this has the other time. Yeah? And the way we can think about this, and there is no unique solution to this, which is a big problem, we have here our distribution, that is a function of f of the microscopic velocity c, and this has somehow to be transformed into, now we use our moments, and in these moments we have a few conserved moments. We have non-conserved so-called hydrodynamic moments. and we have something that in the lattice Boltzmann world is called ghost variables. Maybe you don't want to call them ghost variables. This is just the way they are called in this field here, because they are assumed to have no real effect. Yeah. So the hydrodynamic moments, they are the ones that are related to these binary collisions, and they are supposed to be related to the kinematic viscosity. And here, inside the ghost moments is, so to speak, everything else. Okay. What does conserved mean? So conserved means that pre and post collision is the same. The same conserved quantities. So then this would usually be our mass, and it would be our momentum. And in case of lattice Boltzmann, it will not be our energy, because we have this low order discretization that does not support energy. But in a better discretization it would be. So these things are so-called collision invariants, or collision invariant moments. So then the non-conserved hydrodynamic this comes from the fact that viscosity is controlled by binary collisions. So no multi-particle interaction, only binary collisions are related to second order moments, and they relax with the time scale related to the mean free time. And then there are these ghost things. Ghost variables, they are in general not so easy to understand actually. Also because there are infinitely many of them. So they actually kind of encode the detail we are not interested in, of the molecular interactions. So this has no strong influence on the hydrodynamic behavior. other than driving the distribution to equilibrium. So the thing is, you cannot just ignore it. So meaning is that the time scale is usually not known. So it's difficult to measure this time scale. And one thing in physics that you can keep in mind if there is something that is extremely difficult to measure, then probably it does not have a lot of influence, because the influence is the way how you measure it. Yeah. So if it's no way to measure it, then it probably doesn't matter. Yeah. So you could say that's probably not relevant. And in reality, I mean, just that you cannot measure it does not mean it cannot be measured. So it can have an influence, but yeah, it actually has an influence, but it does not have a strong. So I mean, it does not matter that much how it is doing something, but it is you know, they mix up stuff. So I don't know whether when you are cooking, it makes a lot of difference whether you turn this way or that way, or doing this thing like this. So if you make matcha, Japanese green tea, then you actually have a movement that is this infinity, movement. You have to move the whisk like this, maybe there is a difference in the taste afterwards, I don't know. But in principle, these things are mixing stuff up,
Last time I think I saw somewhere this simulation of like moving like spoon into this coffee cup.
Yeah.
It's the guy from, but it was really, really good. I think it's with like some open, if I know something like that, but the guy posted on this LinkedIn that how you can the spoon in the coffee.
The spoon in the coffee, yes.
Yeah.
So, I mean, there's this big question whether you should. Scientists always use the fork in the coffee because all the spoons are already in the washing machine, in the dishwasher, and nobody has turned it on, right? And then there is the big question whether the fork, because it's a grit, should be better for mixing than a spoon. There's something that you should try to find out using Lattice Boltzmann. Now, okay, how's the time? 15 minutes. How to separate these aspects. So, obviously, as we talked about moments, there would be a moment method. Don't fall in love with it. Moment methods. So, the moments are in principle a linear transformation. So in general, what we have is we have a moment, and then we have some index, kind of what I call here an index function. Yeah, then you do an integration. Now this is the continuous way. To be more accurate, it would actually be, in this case, when we are in 3 dimensions, it's a three integral. So you have a function phi that is function of the microscopic velocity. You integrate this function over the population, the distribution, and this gives you a moment. Yeah. I mean, by definition, so a moment is an integral over distribution. So if you talk, so these things that in Germany, the civil engineers, they have this when you say, okay, what is the moment? So they mean torque, yeah. So Drehmoment, yeah. So because this is the only moment they know, they throw out the Dreh and say this is the moment. Of course, Drehmoment is a moment because it is all the forces that are applied, yeah, integrated. They give you so the distribution of the forces or pressures applied to this object integrated over the Hebel arm, yeah, the distance from whatever you define as a center of this. This gives you the torque or the Drehmoment. Yeah, but there are infinitely many moments. For example, also a mass of a body is the integration over its density. Yeah, is also a moment. The same thing, of course, with momentum. So this, because we have already discretized it, can be written in discrete form for the lattice Boltzmann method, that it would be m phi, now the sum over I, j, and k of a phi I, j, k into f I, j, k. So now we can do a translation between these populations. So populations are the discrete parts of the distribution and the moment. So for example, you have Q discrete populations. Then this means you have Q independent moments. Independent is important because you can define an arbitrary number of functions phi such that you have infinitely many moments, but you only have Q independent moments. So again, we have already said this, but back to the conserved moments. We call M00 is rho, is the sum over ijk fijk. Then we have M100, we call also, sometimes it's written as jx, is the sum over I, j, and k, so the triple sum ICF ijk, M010, jy is the sum of ij, k, jc, fijk, and just for completeness, j set is the sum over ijk, kc, kc, fij, k. So these are the conserved moments. Then the non-conserved hydrodynamic moments. So these are second moments. So second moments, for example, M11, M110 is Fijk. Now this is I, C, J, CFIJK, and we have similar moments M101 and M011. So these are second order moments, but there's also a different way of writing second order moments, namely M200. This is IJK IC square FIJK, and there we have M02 and M002. So you see how they are generated, right? So these things are related to binary collisions, and this is not a coincidence that they are of second order. So then for the Lattice-Boltzmann method, the ghost moments, we have third order. Guys, this is M21, M201, M021, M120, M102, and M012. Do we have another third order moment? We have another one. I mean, I've already written the comma. We have M111. Yeah? So we have 1, 2, 3, 4, 5, 6, 7 third order moments. And then we have fourth order, M220, M202, M022, M211, M121, M112. So we have only 6. We have fewer. I mean, this is due to our discretization. I mean, there are more fourth order moments than there are third order moments, but we don't have all of them. Yeah, we come in a minute to why. Then we have fifth order, M221, M212, and M122, and then we have 1/6 order, M222. So, and now if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. This is the number of populations that we have. Yeah? So now, if you were counting, you could ask yourself, why is there no M300? Because this would also be a third order moment. Yeah? Maybe you already know why. Okay, if not, let you tell me this, there are not only ghosts, but there are also aliens. We have ghosts and aliens. So ghosts, by the way, ghost is a very official scientific term for these things. Yeah? I didn't make this up. The only thing that I made up is aliens, but because I have a name in Lattice Boltzmann, I can make things up and they actually turn out to be then they come, so a few things that I've made up have become official. Yeah. So I now call these things aliens. I know that aliens is a little bit differently written than alias, but it comes from alias, so it's a second name. What we mean by aliens is there are moments like M300, yeah, that you can write as now for that particular lattice. This is for this velocity space. So what I've never written down what the sum is actually going over. The sum is coming from -1, -1, 0, 1. Right? So this is the sum. So and now the third order moment would be defined like this. See, since I can only be -1, 0, or 1, and if you take 1 or -1 to the third power, you end up with 1 or -1. Right? So all that happens here is that this is C times M1, 0, 0. So these two so C is a constant, yeah? So these two moments are not independent of each other. They are actually exactly the same. So we can define as many moments as we want, but we only have this finite number of independent moments. Yeah. By the way, the same thing would happen for any index that is. So the same thing here happens for all the odd indices, but also all the even indices would also behave in the same way. So M400 would be the same as M200 and also the same as M800, right? So there are other moments that with the same name and they are called Elliot's. So in principle now, okay, maybe, where are you? So each non-conserved ghost moment can relax with its own rate. And now there are two problems. I always end up on problems. I'm a depressing guy, I know. So the best rates for the moments are often unknown, or they are difficult to derive. It's not impossible, we have done this, but it's not easy. And the more important part, and this is what we'll discuss in the next lecture, is we have an arbitrary partitioning. So the way we choose our moments is kind of arbitrary, and there's actually not the optimal way, as you can find out. For example, this partitioning, so the partitioning is how you define your moments. Yeah, this is, if you do it the way that I've written them down up there, this is not invariant under rotation. So if you look at this in a different coordinate system, you get a different result, and even more problematic, it's not Galilean invariant. What does it mean it's not Galilean invariant? Any idea what Galilean invariance is? What was Galilei's? So in German school, you always have to read a novel from Bertolt Brecht, who wrote about he was a communist and he was a lot against the church. Now I guess you're probably both not Catholic potentially, yeah. But so.
From Galileo, or
Galileo, but you may have heard that Galileo had problems with the church because he said that Earth was turning. And this is something that the church back then could not agree with. So they had this problem. He had to denounce his own theory, otherwise he would have been burned to death. And actually, this is exactly the thing. The Galilean invariance means that, or it's almost the thing because there's a small mistake in this. What Galilean invariance means is that physical laws should be independent from the inertia system they are stated in. Yeah. So if we have a moving system, if you have a train, you're inside it, or how Galileo described it, when you're inside a ship and the ship is moving, because they didn't have trains, yeah. So everything inside this ship acts as if nothing was moving at all, right? So physical laws inside the ship, the moving ship, are the same as outside the moving ship. It's not completely true that you can translate this to the rotation of Earth, because Earth is not an inertial system, it's an accelerated system because it rotates. A rotation is an acceleration, and therefore the physical laws on Earth are different. So there's a Coriolis force and mostly there's a Coriolis force, but also a centrifugal force that you can measure. So I mean, if I throw something at you, it will not go straight at you, but it will curve away. This is meant with Galilean invariance, and this definition that we have here turns out not to be Galilean invariant. And you see this when you think about back to the pressure. We have a velocity somehow. You have to know the velocity inside the pressure. Now we come again to different definitions of pressure. There's a static and a dynamic pressure, yeah, and the total pressure. And there are these experiments that you see the total pressure is the static pressure plus the velocity there, so the velocity is taken out, yeah. So you can use static or dynamic pressure and both of them are somehow pressures. Okay, we have reached our time and will continue on Thursday, I believe, right? Okay, then.